Hello everyone. Hope everyone is doing well. Like some of you might know, as alumni of the Lebanese University Faculty of Sciences Branch 2 Fanar, our goal is to help the students to gain technical and soft skills and to help them advance in their career. I want to introduce our committee. I, Maribel Al-Kahuf, Chairperson, Gabriella Shible, Vice Chair, Mary Jane Karam, Secretary, Ora Hello, Treasurer, Elie Dina, Webmaster, and our branch advisor, Dr. Marina Wal Sabrajmayel. Elie Dina will be our speaker for tonight. Okay, Elie Dina is a Lebanese University graduate in data science and psychology. He is now undergoing a master's degree in natural language processing at University of Lorraine, France. He worked in different companies in the field of data science, such as UNDP for the project as ARIS 2.0, and now working in a debt collection company in Metz, France, turning his specialization into AI and emotion. Elie Dina, the floor is yours.
Hey guys, I hope you're all doing well. Um, if you remember, during our first meeting, we were talking about uh, data science, machine learning, and how to process data. And as you know, our series uh, of meetings is going to be about machine learning, and we still have two left other than this one. This one is going to handle regression, which is a type of machine learning. So first, what is machine learning? What is AI? What is deep learning? What is data science? So AI is, in a way, the big family that joins everything. AI handles everything that robots can do instead of human beings that can help them. Machine learning are kind of models, functions that help help humans do stuff. For example, um, they learn from data that we have, from surrounding data, and apply their knowledge into it. Deep learning try to imitate the human's behavior as much as it can using neural networks, which try to imitate as well the neurons in a person in the human beings. Data science is the field of handling data with mathematics, and basically it joins all these three fields, and it has a subset alone, which is about data architecture and so on. So whenever we're handling data, mainly pre-processing, exploratory data analysis, this is about data science. And when we're developing machine learning models and so on, this is regarding machine learning, AI, and so on. So the first thing is to differentiate between what is supervised and unsupervised learning. So as you can see from this figure, while we're having supervised learning, there is a student and there is a teacher. So the teacher is supervising how the student is learning. He's giving her examples and so on. Same for supervised machine learning models. So basically, uh, in supervised learning, we would have data and we would have classes. Uh, we would learn from the data that we have, similarities, context, and so on, to be able to differentiate between the different classes that we have. While unsupervised learning, we teach ourselves. We try to figure out by ourselves what are the similarities without knowing that there is a class in the end. So, for example, if we have colors, size, and another feature, let's say dotted, and we know that these are animals. So if we have the name of the animals at the end, So that would be considered as supervised learning. If not, this will be considered as unsupervised learning, as the machine will have to learn by itself. So here's a small differentiation between supervised and unsupervised machine learning. For the supervised learning, the output is known. So as I said, these are classes. We would know if, for example, if the animal is an elephant, is a giraffe, and so on. While regarding the unsupervised learning, we do not know it. The data set is called labeled in supervised learning, while unlabeled in unsupervised learning. The method of learning, as you can see, and directly by the name, supervised and learns by itself. The complexity is simple in supervised learning, while it is complex in unsupervised learning, and that's because the machine will have to do all the possible scenarios, will have to calculate so much more regarding unsupervised learning. Supervised learning tends to be more accurate than unsupervised learning. And the main question that you might ask yourself, when do we use unsupervised learning? Why don't we label the data ourselves? And we're going to respond to that in more details during the last session. But basically, we tend to focus on unsupervised learning when the annotation takes a lot of time and there is not enough time to label all the data, or there is kind of different opinion on how to annotate, and so on. So the main types of supervised learning are regression and classification. During this session, we're going to talk about regression, which is basically what we took in math in high school. We have to predict a continuous outcome variable called y based on one or multiple values, variables called x. So here you remember kind of y equal ax plus b. So that's the idea of regression. While regarding classification, we would group classes, which are the outputs, and even y in the regression is considered as the output, based on the similarity of the features, which are called the inputs, which are the variables, which is x. And this is going to be the next session's topic. Mainly when we work in machine learning, we need to divide our data into a training set and a testing set. And while we need this differentiation, why? First, for the model to learn on the training set, to understand what is happening in the world and so on. And we test it on the testing set to know how much accurate it is, if it was able to understand correctly or not. And how do we do that? We by comparing the prediction and the actual value. So when we create a model, obviously it cannot fit the actual output 100% of the time. So it is possible that it gives some variations. And when we have this, there will be some difference between the predicted value of the model and the real value of the model. And here we compare them and we calculate different error metrics based on whether it is regression or classification or unsupervised learning tasks to be able to see if the model is doing well or not. So what are the types of regression? There are different types of regression, and the main ones are these four present here. We have simple linear regression, multiple linear regression, polynomial regression, and some type of regressors. And we're going to go through each one of them to be able to mention more and more. But first, we need to talk about some vocabulary regarding regression. So first, so as you can see, we have all these different words that are specific to regression, like bias, variance, underfitting, overfitting, independent variable, and dependent variable. So these are not only considered for regression, they're mainly as well supervised learning vocabulary, but in this case, we're working on them mainly for regression. So for example, the independent variable or variables are the features, are the inputs, are the x values that we give the model, we feed the model to be able to understand the data and to be able to calculate the dependent variable, which is the result, the output, y. So if you remember the first equation that I mentioned, which is y equal ax plus b, so y would be considered as the dependent variable and x as the independent variable. What is underfitting and overfitting? So mainly uh, when we're working on data, uh, the model will try to fit what we have into the actual data that we trained it on or not. So if the model perform better in the testing set and not in the training set, this means that there is an underfitting. And here the machine learning is too simple and is not able to capture the underlying structure of the data. While the overfitting, it's when the model is have better result in the training data rather than the unseen data. And here we fall in the problem of overfitting. Regarding the bias and the variance, these are both are used to know if there is underfitting or overfitting. And the bias is the simplifying assumptions made by the model to make the target function easier to approximate. So the main differences between the predicted and the actual value, while the variance is the amount that the estimate target function will change given different training data. And here we're talking about the standard deviation and so on, how it will change based on the training data. I'm sorry here the picture is quite small. I didn't pay attention to make it bigger. But basically here we can see in the first figure at the left, we can see that we have kind of underfitting. The linear line, or sorry, the straight line is not fitting correctly and not taking into consideration all the points. And we can see that there is a high difference between the points in the line and the green points. And here we can see that there is a high bias and low variance. While the middle picture show a straight line in the middle, which seems to be better. And here we do not consider that we're falling into neither overfitting or underfitting. While at the end, we can see that the line that we have, it is kind of following each point and so on. And here we are falling into overfitting, which is a main issue as well. And we have in that case a low bias and a high variance. So as I mentioned, when we have underfitting, it is poor at training, poor at predicting, but sometimes it can be better at predicting than training. And this is also bad. While for overfitting, it is good at training, but poor at predicting. So now we're going to talk about the simple linear regression and what it is. So as we mentioned, y is the output, the dependent variable, and x is the independent variable. So while working on simple linear regression, basically we're taking only one independent variable and only one dependent variable, and we check this relationship between them. So some people call it correlation as well. So we consider this. And here we have the formula, which is b1x1 plus b0 plus epsilon. And b1 is the slope of the line, which is, if you remember the first function that I mentioned, ax plus b equal y. So the a is the slope of the line, how the line is varying. If it is positive, then it is increasing. If it is negative, it is decreasing, and so on. And b0 is the intercept. And the intercept mainly is where the line begins if x equals 0. And there is also this error value, a small error value, because the model will not be able to fit everything perfectly, especially when we're working on linear regression. So for example, here, we're taking if a model, which is, we're doing a model, and we're showing the linear regression between income and happiness. So we're checking if people with more income are more happy or not. And we can see here that it is kind of an increasing, increasing. People with more income will be more happy. And here we say that the data, that happiness and income are correlated. And here we can see that we have the equation 0.2 plus 0.71x. So this line here has a slope of 0.71. And when the income is 0, then we would have uh, a happiness score of 0.2. So that's it. Regarding multiple linear regression, it is the same principle of simple linear regression, but instead of working on one independent variable, we take many independent variables into consideration. So for example, we want to calculate the salary based on the years of experience, based on the age of the person, what's their higher education, whether high school, bachelor degree, master degree, PhD, and so on. So it is the same kind of function, b0, which is the intercept, b1, x1. So b1 is the coefficient of the first variable, which is, for example, in that case, years of experience. b2 is the coefficient of the second variable, which is age. b3, the coefficient of the third variable, higher education, and we go on and on until we get all the needed variables. And bn, as I mentioned here, are the weights of these variables. So for example, here we're taking into consideration mileage in cars, and we take into consideration also weight and horsepower. So as we can see in this graph, it is a 3D graph taking into consideration all of those together. And we can see as the, for example, as the mileage with a higher mileage and the lower weight, with a low weight and a low horsepower, we would have a higher mileage, and a decrease while the weight and the horsepower increase. So we would have, this is, for example, which we can understand. Unfortunately, we cannot plot graphs in more than 3D dimensions. So it would stop here, but it's not as representative as 2D. So that's why we take into consideration 2D plots, and we try to show the different variables in different ways. And that's what we're going to see today in the hands-on that I've prepared. Polynomial regression is similar to linear and linear regression, but the main difference is that it takes into consideration that we have degrees. So we can have to the power 2, to the power 3, to the power n. And the degree of the equation is the nth degree of the polynomial. And we choose while working on the model, we choose which degree is the maximum degree that you want. And obviously, as we increase the polynomial degree, we would be increasing the complexity of the computation. So for example, here, we can see that the line is not straight as we have seen in previous examples. And it's because the model is polynomial. And we can see here the intercept is 944. The coefficient of the first of x is minus 1.15, and so on. Okay. Then we would have as well regressors. And regressors are also known to be used for classification, but tuned for classification. Here in this case, I'm sure you've heard about decision trees, random forests, KNN, and classification. You can also use all these models in regression, and there is you can check websites such as sklearn and so on to be able to check the codes, examples, and more. So which model to use? And this is a very important question. The thing is that while we're working in machine learning and data science, we cannot always say, okay, we use this model for this task, this model for this task. And it is quite unfortunate because we have to experiment. And obviously, we can check previous studies, previous work done, state of the art about a specific test that we're working on, and check how it was done, and which models were used, which models were not used, and check the reasons behind them. But mainly, you are not able to know this unless you do a very deep EDA, exploratory data analysis, and you try to experiment with both of them. And here, for example, what I've given you is as an example, is to visualize the data. See the relationship between the dependent and independent variable. So for example, if we take this example here, we can see that the data is not following a straight line. And here we can check that no, a linear regression would not suffice, and we would need a polynomial regression. While in other cases, like for example, in that case, we see that it's following kind of a linear trend. So that's why we go for a linear regression and so on. And at the end, I would advise you to try all the models that you think might be possible, might work, like uh, different kind of regressions and so on. So you should be able to try it, and you should have fun trying them, because sometimes they're not computationally complex, they do not take much time, and they're quite easy to find a guideline, not just a guideline as well, to find a skeleton of the models, which you fine-tune while working on hyperparameter tuning. And we're going to check what is hyperparameter tuning later on while working on classification. So, as I mentioned before, the data is divided into a training set and a testing set. And we tune the model, we fit the model on the training set, and we test if it is correctly working on the testing set. And to be able to check if it is correctly working, we need to calculate some metrics comparing the prediction score and the actual score. And in that case, we would compare the mean squared error. For example, in regression, basically, we calculate one of these 4 regression metrics, which are the mean squared error, the root mean squared error, the mean absolute error, and the coefficient of the determination, which is R squared. Regarding MSE and RMSE, they're quite the same, but the main difference is that RMSE is the square root of MSE as it can be determined from its name. And it is useful when we want that the error metric to be in the same units of the target variable, for it to be more understandable and more representative of the data. While the mean absolute error is less sensitive to outliers. If you have a data that has a lot of outliers and you are not able to remove these outliers, we would consider using the mean absolute error, as it will avoid the influence of these outliers in the error metric. And in the end, R squared, it measures the proportion of the variance explained by the model, like how the error is variating, if the model is a good fit or not. So first, regarding the mean squared error, so it calculates the average as the square difference between the predicted outcome and the actual outcome. And as we're working on square, so it would not differ if you're taking predicted outcome minus actual outcome or the inverse. It is the same. So n is the number of samples that you have in your testing set. So for example, let's consider you have 20. And then you would differentiate between these 20 outputs. Like you would have uh, 5 for as actual and 6 for the predicted, and you do 5 minus 6 squared plus and so on. You join all the different variables, all the differences squared, and then you divide them over 20. The RMSE is the same concept. It is only the square root. So you basically just add the square root. Regarding the mean absolute error, it focuses on the absolute difference. So it would always give a positive value. It is preferred to use when we don't have, when we have a lot of outliers. Otherwise, we would use MSE. And in the end, the coefficient of determination, which is the R squared, it measured the proportion of the variance in the dependent variable, which is Y, that is predictable from the independent variable. And this is the function which basically do the so kind of sorry. So the actual outcome minus the predicted outcome squared over the actual outcome minus the mean of the actual target. So we would have the all actual targets that we have. We would add them, divide them by the number of samples, and squared. And the value that we obtain here, we would 1 minus the actual the value that we obtained. And that's how we calculate the R squared. Regarding, so as I mentioned before, we fall multiple times into underfitting and overfitting. And that's why we need to regularize our models, because in regression, there is not much hyperparameters that we could focus on this like classification. So the parameters that we have in regression are the number of inputs that we have, the inputs that we have, and that's it. To be able to make the model less complex and to be able to address overfitting specifically, we use regularization methods. And there are 3 types of regularization methods: L1 regularization or lasso regression, L2 regularization or ridge regression, and at the end, elastic net regression, regularization. So lasso regression, also called least absolute shrinkage and selection operator, it is a regularization technique that adds a penalty to the linear cost function. So at the end, you would add a penalty to know how to say that, okay, uh, the model should learn better. And I'm gonna explain more about this right now. So here we're not just it's not only the MSE. It can be any cost function. So it can be the RMSE, MAE, R squared. It's based on whatever you like. And basically, when we're training the model takes chunks of data and do not take the whole data at the same time. It trains over a small part, then a second part, then a third part, and every time it learns on a new type of data, it checks the how much variance, how wrong it was before, and then continue learning until it make the actual value of the MSE of the cost functions smaller and smaller. And by adding this penalty, we're telling the model, well, we're adding a small penalty for you to know that there is more errors than you assume, and for you to train better. And mainly when we're working on regression, the main thing that we're focusing on is the gradient descent, which is going to be a topic for another time. Ridge regression, sorry. So in lasso, in lasso regression, it takes the sum of the regression coefficients in absolute value. And P is the number of features that we have. So for example, as I gave an example in multiple linear regression, We have age, years of experience, and higher education. So we have three features in that case, and thus we would have three different regression coefficients. So to add them all in a to obtain a positive value, and add a regularization parameter alpha, which can differ between 0 and 1, and then add it to the MSE. And then the concept of ridge regression is kind of the same. The only difference is that the regression coefficients are added, but the squared of this regression coefficient is added, not the absolute value. At the end, elastic net is a regularization that takes into consideration both the ridge regression and the lasso regression. Add both of them together to be able to distribute between both of them, because each one of them focus on something different. The main difference between L1 and L2 regularization is that for the least important features in L2, we would not nullify the coefficient, but we would make it really low. So for example, if we take the example of, let's take this one. So instead of having 0.1 in that case, as if it is low, the L2 would give it, for example, 0.05, while the L1 might give it a 0. So that's the main example. So here's the main idea about the topic today. And this is a small introduction about regression. And now what we're going to focus on is the hands-on. Last time during our meeting, we focused more about on theory, and we didn't do much actual coding. And then this time, I already did the codes, and we're gonna go through them and check how they're done, how what are the codes, what are the libraries, and in the end, talk about how to proceed with it step by step. So, and now what I would like to do is have a conversation with you. So, you've all been in our last meeting, I think. And can anyone tell me a few steps of how we proceed with the data? So, what should we do first, and so on? You can open your mics or write them down in the chat. So first we read the data set. After reading the data set, what should we do? So first, yes, we would import libraries to be able to read the data set. So for example, to read a CSV file or otherwise, we would import pandas. We would work on the EDA. Can you elaborate what is EDA?
By ADA, I try to see the features about this data through a simple statistical analysis, for example, to see it could also help me for the machine learning model, as you previously said.
Perfectly. So EDA, which is exploratory data analysis, basically, as Joseph mentioned, do some statistical tests, some graphs, and so on, to be able to understand the data that we are working on, to check if we need all the features, if we need to remove some of them, and so on. Someone else, can you tell me what should we do after the EDA? So what's the second step that we should do after EDA and before beginning with machine learning? So yes, we would draw the CSV, would plot them to visualize. So the plotting is considered as part of the EDA. We would clean the dataset, which is the pre-processing part. We normalize the dataset using min-max normalization. We could use scaling and so on. There are different stuff that we can do. as the data as numerical. Try to convert descriptive data into numerical data if possible as well. That's also considered part of the pre-processing. That's perfect, Rafael. So for example, regarding the conversion of descriptive data into numerical data, here we can take into consideration different stuff. So we could, if we are working with binary data, for example, male, female, we would work on transforming male into 0 or 1 and female into 0 or 1. So that would be the first one. But in other cases, while we have different descriptive data, for example, we would have, for example, let's take the geography of Lebanon. We would have the north, the south, Bekaa, Beirut, and so on. So for example, we took 4 main examples, and here we have 4. So instead of, we could go through the basic one, which goes 0, 1, 2, 3, 4, or 0, 1, 2, 3, basically, sorry. Or we can work on something called one-hot encoding. And regarding one-hot encoding, what it does basically is it gives a colon for each one of them. So location Beirut, location Bekaa, location north, location south. And it would give a 1 wherever there was Beirut in the colon Beirut, a 0 whenever there was not this actual value, and so on. So as well as Anthony mentioned, we would check if there is any missing values. That's perfect. So if there is any missing values, what should we do? Can anyone let me know? The data variables, if they are correct, perfectly, because in some cases we can compare between them. So for example, if you have age and we have birth year, we could compare to check if it is correctly done or not. Check the shape of the data perfectly. So when we talk about the shape of the data, we say the number of columns, the number of rows. So what about the missing values? So if we have missing values, what should we do about these missing values? We would replace them with the average value. Okay, that could be an idea. How we would replace them, as Anthony mentioned, we would fill them with the median, and if descriptive, with the mode. And here there is a small the answer is not complete about what you said, Anthony. So when we're working on numerical data, we can fill it with the median or the mean. If the data is not following a normal distribution, we mainly fill it with the median. Otherwise, we would fill it with the mean if it is following a normal distribution. But in some other cases, we do not bother ourselves with replacing the missing values. We just do not care. We have a lot of data, we remove them. So that's it. In some as well, there is, so regarding the pre-processing part, there is a lot of stuff that we can do. There is a lot of stuff that we can consider. Yeah, that's true. So for example, males and females cannot be replaced, but these are not numerical data. These are descriptive data. Okay. Because in that case, we might be falling into a bias or giving wrong information, especially when we have males and females 50-50. So that could be an example. So in these kind of examples, we would just remove the actual row and that's it. As well, we can take into consideration to check if there is any duplicate values. I'm gonna write it down so you can have it. And when we have duplicate values, we directly just remove them. Or if we have different duplicate values in which some of them contains missing information, we would fill the other missing information based on the actual duplicate value that we have. And how do we check if there is a duplicate value? As you know from database, most of you, I think, there is something called the primary key. And the primary key is the value that cannot have any duplicate. So whether it is an ID, so it can be one primary key or multiple keys forming one primary key. Okay, and as well later on you could check outliers and so on and so on and so on. So there is a lot of pre-processing that you can do, but mainly that's what we mentioned here. So after the pre-processing, so first we said we would import the libraries, we would read the data set, we would do the exploratory data analysis, which visualize the data, check the data, the analysis, the statistics, and so on. We would go through the pre-processing. Then we would divide our data into a training set and a testing set, basically to train the model on the training set and test the model if it is correctly working on the testing set. So that's it mainly. And in the end, we would build our models and test if they are working correctly. So now back to what we have. So, okay, that's it. Perfect. Guys, could you let me know if you're seeing the screen? Can anyone unmute themselves and tell me if you're seeing the screen to make sure that we can continue?
Yes.
Okay, perfect. So here first, so this Google Colab is going to be shared with you. So it is the code that was done. I did the code and so on. So you could have it later on at the end. If you want to train stuff, if you want to change some stuff, you want to hyperparameter tune, and so on, so on, so on, so on. This is a basic first step. And obviously more tuning, more cleaning, more information processing can be done. And this is what you're gonna have to do for the next time. So first, we would import the libraries, for example, pandas to be able to work on the data frames, NumPy to be able to work on the actual values, and later on for the machine learning, Matplotlib and Seaborn, which are used for visualization. And sklearn is mainly used for all supervised learning. And we would have the different sub-libraries in them. So for example, the model selection, which give us the the function train test split, which divide the data into a training set and a testing set. The linear model, which would give us the linear regression, whether it is simple or multiple linear regression. The metrics, which would give us the R2 score, mean absolute error, and mean squared error. And in the end, we have as well the polynomial features, so to do polynomial regression, and the pipeline to be able to do the polynomial regression as well. So so that's what Joseph said. In the beginning, we begin with importing the libraries. Then Raphael continued and mentioned that we would have to read the data frame. So our data frame is present in on my drive, and I have two here, for example, and I took into consideration the first one, which is insurance one. It is a CSV file. So first, we would begin with what Raphael and I'm trying to remember the names, Raphael and Anthony mentioned. So we would go through both of them. So we would check the name of the colleagues, for example. We have unnamed 0, age, sex, BMI, children, smoker, region, charges, and birth year. And the end goal of this project is to calculate the charge of the insurance, how much we pay the insurance, how much insurance would pay based on the different information, which is age, sex, the BMI of the person, how many children they have, if they are smokers, in which regions they do live, and so on and so on and so on. So we would describe the data, we would check the shape of the data, and can anyone tell me which one is the number of columns and which one is the number of rows? So this is going to be we're gonna talk together. So I would like some of you to unmute themselves, try to participate. So So we're not in class, guys. I'm not gonna be like a teacher and I'm gonna be like checking a name and telling you guys. Okay, perfect. So we have 1,338 rows and 9 columns. And could anyone tell me which ones from these are numerical data and which ones are objects? So as we mentioned in the first session, we have object data, which is the descriptive data, and we have numerical data. So can anyone tell me before going at the next step, which ones are the numerical or which ones are the objects? Responded. Okay, smoker, gender, region, and are descriptive. Yes, that's correct. So let me check. Smoker, gender, and region. Yeah. So gender, smoker, and region, these are all, as it seems, they are all descriptive. But in the same time, Rafael added in the end the word I guess. And this is very important because in some cases, the data set might not be actually correct. So the BMI might be written between quotes, and which would give them as strings instead of actual numerical data. This might hold a problem. Other cases, if so, basically the data is entered manually in many cases, and we might have additional written information. So, for example, someone might write age 19 or 19 plus, or so on and so on and so on. So these would fall under the category of object descriptive data, while they are actually not. And here is when we should do the processing, the pre-processing, and clean the actual data. So first, we would do the description of the data. And for example, for the unnamed zero, we see that we have 1,338 values, and basically we have for all of them 1,338 except for the BMI, which seems to have 3 missing values. And we can see the mean, the standard deviation, the minimum, the first quartile, the second quartile, which is the median, the third quartile, and the maximum. And basically from these 5 values, we could plot the box plot. Okay, the whisker and the wisp, as some might call, or the mustache. So that's it. And this can help us to see if the data is actually normal or following a normal distribution or not. So let's continue. So here is the part of the numerical data, and regarding the objects. So as Rafael mentioned, we have sex, smoker, and region. And we can see that for gender, we have 2 unique values, which are male and females. For smokers, we have 2 actual values, which is no and yes. And for region, we have 4. And in that case, we can see that we have southeast at least, and the other ones would be southwest, northwest, and northeast. And we can see the top ones. So we have male, which is more present than females. It has 676. And to calculate how many females we have, we can just basically do 1,338 minus 676. And the same for the others as well. Now here, regarding the histogram. So I'm going to explain the code. In histograms, we have something that is called bins. And these bins are the difference between this point and this point. This is a bin. And here I took into consideration the bin from 15, so age minimum is 15, until the maximum age. And we add 5 each time. So for example, we have 13 to 20, 20 to 25, 25 to 30, and so on until the maximum age. The maximum age might be like 62, but we take 65 because we're incrementing by 5. Okay? Then we plot the histogram. This, if we run this by itself, it would give us an empty plot. And now we're saying that we want to plot in a histogram the age with the number of with this number of bins. With its color sky blue, we can change it to red, and the edge color black, and we can change it to have whatever we want. This code that we have here is to add at the top of the bar, at the top of the histogram, the how many we have, and that's it. And this code is basically where to position the text. So it would take the width divided by 2, so it would be in the middle at the height, and we add 0.2, so it's not in the middle of the line, and so on. And in the end, we would have the title, which is histogram of age, the X label, which is the X on the X-axis, the Y label, which is the frequency, the ticks, which are the bins. We have, as mentioned, 15, 20, and so on. This line style is to be able to add these, and the alpha is how transparent these are. So if you had an alpha of 1, this means that it would not be transparent, while if you have an alpha of 0, it would be very transparent. So here we can see that the age is not following any kind of distribution. It seems to be quite okay. It is kind of standardized, like we have as many people from each age range, so that's good. Let's continue. Now, as we have seen that we have age and birth year, and as we all know, there should be a correlation between both of them. And we can see from this heat map, so basically we use heat maps and correlation matrices to be able to show these values. And we can see here between the age and birth year, there is a correlation of -1, which is a perfect correlation. And what is that? This means that when we're talking about a negative correlation, when one is incrementing, the second one is decreasing. So basically, in that case, the birth year varies between 1955 and 2019, I think. So the age would vary accordingly. And we can see that the person who was born in 2000 have an age of 19, while the person who was born in 1955 would have an age of 64, for example. So so while the birth year is increasing, the age is decreasing. And as we have a correlation between those, while doing the model, we can remove one of these. We can either remove the birth year or the age. So you choose whichever you want. I'm gonna make sure if anyone has any question. So if you have any question, don't be shy. You can directly ask. You can unmute yourselves and so on. Then we're plotting the distribution of BMI. So the BMI is mainly to see if someone is obese, is slim, is healthy, and so on. So we can see in that case that we have a BMI that is variating, and we can consider the ones after 50 are outliers. So for example, yeah, so basically we have 50, 55. But otherwise, we can see that the BMI is actually following a normal distribution. It is not skewed to neither to the left nor to the right. So that's a good thing. So as you remember, or if you remember, basically, we have 3 missing values in BMI. So we can either remove them because they're only 3 values, and we do not care much because we have 1,000 data left, 1,335 data left, or we can actually fill them with the normal, with the mean value. So both applications would be correct. Otherwise, if we continue, for example, now we're checking the colon children and how many children we have. So we have 574 people with no children, 324 with one children, and so on. And obviously, we should plot them. And can someone tell me in which type of plot should we plot them? What is the type of the plot that should be plotted? Pie? You can, you can work on a pie chart, but what kind of other plot as well we can use? And no, when we're working on discrete data and not continuous data, it is preferable not to use histograms. Histograms are used for age, for example, for BMI and so on, because these values are continuous. For discrete data, such as the number of children, this is different. So not histogram, but quite similar, which is, I believe in you guys. You can remember. What is similar to a histogram but don't have the bins touching? A bar plot. Perfect. No, so the histogram as for example, okay, so this is a histogram, and here we can see that the borders are touching, while and this is a vertical histogram. A bar plot is that. So it is very similar to a histogram, but the main difference, these are not touching, to be able to separate between discrete and continuous values, because you cannot have half a children, but you can have 19 and a half years. So this is an example. So that's it. And we can see that it is decreasing. People with 0 children are far more than people with 5 children. So that's a point that we should take into consideration. And regarding the horizontal and vertical debate, so we would use a vertical bar plot whenever we're working on any kind of data. But when we want to check the top data, so which one are the tops, we would use a horizontal bar plot. So for example, if you want to check the top sales cars in US for 2021, for example, we would do a horizontal bar plot and see the first one, second one, third one, and so on. But whenever it is not a top, when we're not checking which ones are at the bottom, which ones are the top, we use a typical vertical bar plot. Okay? So basically, we're kind of repeating the same thing. So for example, for gender, we took into consideration a pie chart, as Raphael gave an idea before. So we can see that it is kind of balanced. We have 50.5% males, 49.5% females, and this is actually good. We continue and we see, for example, regarding smokers, and it represents the actual word. We have many non-smoker people, while we have very few smoker people for it, accordingly. So in that case, we have 20.5% of the people who smokes, while 79.5% people who do not smoke. So that's it. Regarding region, we did the same thing, and we can see that it's also balanced, very similar. Like we have approximately 25% for each northeast, northwest, southwest, and southeast, and this is actually a good thing. So we could remove the region. It is possible. Now the distribution of charges in US dollars. And we can see that basically the charge, okay, so sorry, more people have few smaller charges than others, so it is decreasing. So now we want to see if smokers have more charges than non-smokers. And as we can see from this plot, so for example here, we selected the smokers from the data, the non-smokers, we created the plot, we added the first subplot for smokers, and so on. And we did something called a subplot. If you remember, during our first session, we called subplots, which is a big plot containing the different plots that we have. And in that case, we can see the difference. Here are the smokers, and basically, sorry, what happened? Sorry, okay. So as we can see that we directly began for smokers a charge of around 10,000, while for non-smokers, the beginning of charges was around 5,000. So we can see, or we can already say, that smokers have more charges than non-smokers, and this is correct because mainly smokers have more health problems than non-smokers. Okay, and that's why the insurance would have more charges for smokers. While for sex, for example, we wanted to see if there is a difference if females have more charges and or not, and we can see that it's approximately the same, so which is quite okay. But now we want to compare regarding the age and regarding, so here what I mentioned before is that we try to show in one plot 3 different features instead of having them in a 3D graph. So we take into consideration the age in color, sorry, so the smokers would be represented in color red, while the non-smokers would be represented in color blue. And we took into consideration not just the age and the charge. And we can see, so the charge increase with the age. It's not a very high, it's not a very high increase, but still, it is a small slope. And we can see for basically for smokers, all smokers that we have a higher charge than the most non-smokers. So we can directly understand from this data, if you are a smoker, you would have more charges for the insurance than non-smoker. So stop smoking, guys. Now here we're taking into consideration BMI. So if the person is obese, overweight, healthy, or underweight. And seeing from this graph here, which is not stacked histogram, it is an overlapped histogram. We can see that obese people mainly have more charges. So first, this data set represents more obese people than overweight or healthy or underweight. Like there's very few, very few underweight people. There is quite okay number of healthy. Many more are overweight or obese. So this data set represents more obese and overweight. And that might be due because overweight and obese people might need an insurance more than healthy and underweight. But you can see that obese people have much more to pay than underweight, healthy, or overweight. And this might be due to either a bias in the data set. So if we take more overweight, healthy, and underweight people, we would have more a more balanced data, and we can see the trend that is kind of going the same. Or it's not. It is really that is the case. So which we also taking that into consideration. So here is regarding the EDA. Does anyone have any question regarding the EDA? Is anything not clear? Do you want me to go over something again? I'm gonna wait for response before moving on. Is it a yes? Is it a no? Are you still with me? Okay, deal. So let's continue. So after the pre-processing, as we said, we're gonna go through the after the EDA, we're gonna go through the pre-processing, and which is the most important part. And you should remember that EDA and pre-processing takes 80% to 90% of the time while you're working on machine learning. So this is something important to remember. So first we're checking how many null values we have, and as we remember, we have 3 BMI that are null. And in that case, we said because the BMI is quite following a normal distribution, we can fill them with the mean. But if it was skewed, we would fill them with the median. And in that case, I would prefer just to remove them because there are only 3. There's not much more data, so it is okay to remove them. And here it is what we did. We dropped the NAs, and then we checked that every single one's removed. So that's okay. If you remember, the unnamed 0 showed is basically the ID, which would not add any actual interest into the data that we're working, so we can drop this column. And because the age and the birth year are highly correlated, highly negatively correlated, we can remove one of them, and I decided to remove birth year. You can also try to remove age and leave birth year. You can try it and see how it might vary. So we drop both these columns, and then, as I think Raphael mentioned, we are mapping the categorical, the descriptive data into numerical data. And basically, we would change female into 0, male into 1, smokers no to 0 and yes to 1, southwest, southeast, northwest, northeast. And here you can do whatever you want. You can change them however you want. You can put southeast 2, northeast 0, and so on. This is your choice. Or for example, here as well, you can do one hot encoding, or HE, which is one hot encoding. So as I mentioned, one hot encoding would be basically just dividing the columns, dividing one column into n number of columns. So for example, in that case, we have 4 unique values, southwest, southeast, northwest, northeast, and we would have 4 columns with each name. So regions, southwest, region, southeast, and so on. And we would have a 0 we would have a 1 wherever there is any of these values. So here we did the mapping and we changed the values. And we can check that all of them now are integer or float. So the BMI was a float, the charges was a float, and everything else is an integer. So that's the pre-processing. Do you think, guys, that more pre-processing can be done? What could we do as well? I think someone gave some examples. I think either Raphael or Anthony, I'm not sure anymore. Yeah, so it was Raphael. So what step as well can be done? Let me know, guys. There's one step I didn't do. Yes, perfect. The min and max, min-max scaling. So I'm gonna write them here. So An additional step that you could do is normalize the data. And there are different ways to normalize the data. So, for example, as Anthony right now mentioned, and prior to that, it was Raphael. You can work on max scaling. That's an example. You can work on just a standardization. Or you could do normalization. And your kind of assignment to next time is to try all these three normalizing methods on the data, because they differ one from another. And I'm gonna share with you, when sharing this, I'm gonna share with you a Google form in which you would fill what is you would answer what is the correct answer for min-max scaling, what is correct regarding standardization, what is correct regarding normalization, and you would give me a small description about the model that you used, on which values you did standardization, normalization, and so on, and the error metric that you obtained. So, for example, you tried MSE, you tried the model on MSE, what is the value that you got for training and testing. So that's the example that you should do. I'm gonna share with you the Google form, I think by tomorrow, hopefully. Okay, so now regarding the machine learning processing. So as we first said, we have to divide them into a train and testing set. And that's what the train test split does. It divide them based on X and Y. X is everything except the output, which is the charges, and Y is only the output that we have, which is in our case the charges, the target variable, and so on. Here in that case, we have 0.2. We took into consideration 0.2 as a testing size. So 80% of the data is training set, 20% is testing set, and the random state is kind of a location in your computer. And each time you run the model, it would take the same 20% that you had and as testing set, and the same 80% as training set. So the MSE do not differ each time you run your code. So the random state, you can do whatever you want. I don't know why by default it's 42. You can put it 1, you can put it 100, you can do whatever you want. This testing set, the testing size is also by default in many cases 20%. You could also try to work on different stuff. You can try, for example, try the testing set size 10%, for example. Okay, 10%, 30%. Maybe the leave one out method. And basically, this leave one out method, you train on everything and you just test it on one point of the data. So all these are possible. And we wanted to see the shape of the data. So 80% represented by 1068. And we have 6 columns, which are age, sex, BMI, children, smoker, and region, and so on. Now here, we're taking into consideration the linear regression. And because we're working on 6 different variables, features, we are working then on multiple linear regression. So as I told you, you should try to predict on both the training set and the testing set. And why is that? Because we need to check if there is overfitting or underfitting. So I used the functions that were given by sklearn, which are mean absolute error, and so mean squared error and R2 score, and to be able to calculate the RMSE, you basically just do the square root of the MSE. So that's it. And these are all in the library sklearn.metrics. And here we can see we have an R2 score for the test set of 0.8, while for the training set 0.73. The MAE, that's the result. The MSE, that's the result. And the RMSE, here's the result for the training and testing set. So now we're seeing these values and we're like, wow, what does it represent? Can anyone tell me if these values make sense, yes or no? So yes, we would correct Raphael. We would do normalization to decrease the scope of values. I know you're tired. It's been an hour and a half approximately, but I need you to focus for the 10 minutes. So do these values make any sense? I'm going to show them back to you. So no answers? Let me see if I'm not wrong. So the train is, so okay, this is not accuracy. The accuracy, there is no such thing of as accuracy in regression. Accuracy is only considered in classification. So okay, that's good. But what I was mainly asking was about the MAE, MSE, and RMSE. So does anyone have any idea? If you're typing, just like raise your hands, do a reaction just to know. If not, so let me know, guys. Okay. I think no one. Okay. So basically, these values make sense in this data set that we have. Why? Because as we have seen before, the charges vary between, we're gonna go up. Okay. So the charges vary between approximately 5,000 and 60,000. And the MAE, the MSE, the MAE and the RMSE basically compare or check how much it variated. And because the charges is so high, it varies between 5,000 and 60,000, and it's mainly focused between 10,000 and 20,000. So this RMSE is quite okay, but at the same time, it is not a very great values. It's not a great value. So that's it. The MSE makes sense to be that high because it is the square. It is squared. It is the squared value. Okay. So I tried something else. I removed the sex and the region from the features that we're working on. And I wanted to see if there is any difference. So if you remember here correctly, you have 73.1 and 80.5. And if we take here into consideration, it's approximately the same. So removing these values did not change anything. And if you can see here, sorry, this is the, okay. So if you can see here, we have the equation. So here's the intercept. Here's the coefficient for age. Here's the coefficient for the BMI. Here's the coefficient for the number of children. And here's the coefficient for smoker. So as well. Now taking into consideration a polynomial regression. So if you remember, a linear regression basically works on a straight line, while the polynomial regression have these small curves that it might follow. And here in that case, we could see that we were able to obtain a better results, like 0.88 instead of 0.8 and 0.83 instead of 0.73. So this is way better. And we can see that the error decreased quite a lot. It decreased from 6,000 approximately to 4.5K. So this is very good. And we can say that a polynomial regression is a better fit than else. Okay. So that's okay. So here we took into consideration a degree of 2. So we would stop at x to the power 2, or multiplying age by BMI, or age by children. Age was smoker, BMI was children, and so on. I also tried another step, which is taking the degree equal 3 and see if there's gonna be any change. And honestly, it gave me approximately the same result. And that's mean that we could stop here with a degree of 2, with a polynomial of degree 2, because otherwise it would give us a more complex calculability. So that's everything regarding this session. What I would like you to try, as we're gonna share with you quite soon the recording and everything else, the PowerPoint and these codes. And as I mentioned, what I would like you to do for you as well to be able to obtain the certification in the end, I'm gonna be as well sending a Google form in which you're gonna respond on some questions regarding min-max scaling, standardization, normalization, and try to do at least one of them and run the models and have a small description about how you run it and what normalization you did and so on, to be able to show that you were able to understand. And of course, you could use the internet. There is a lot of stuff where you can check it out. So for example, at sklearn, for example, polynomial regression. And here, whenever you go, you can see the different values that you have, for example, degree, interaction tool, the order, and so on. And you would have a small example of it. So that's it. Yes, MSE is big, so the dispersion is great. That's true. And the reason for that is mainly because, as I mentioned, because the values are quite big. And if you try to do the normalization, even on the normalization on the charges, you might be able to, you will see that you'll obtain a very small MSE. But in that case, you'll have to do a inverse normalization to check the actual MSE and to check the actual values that you'll be able to get. So this is also important. Does anyone have any question? You would like to ask anything? You're welcome. I hope you enjoyed this session. I hope it was beneficial for all of you. So I think we're done here. If no one has any question. Sorry, Rose, do you have any question? Okay. So I'm gonna send again my email. If anyone have any question, they can ask me on my email. And that's it. I thank you for coming, and hopefully we're gonna see each other in the next meeting, and we're gonna tell you when. It's gonna be about classification. Goodbye, guys.
Goodbye.
Bye bye.